And for the final talk of the session, Thomas Haas is going to tell us about their work on static analysis of memory models for SMT encodings.
Yeah, thank you for the introduction. So my name is Thomas Haas, and this is joint work with my colleagues from TU Braunschweig and Huawei. So, let's start with a typical verification approach. Say you're given some program and you want to verify it against the specification. And maybe you don't even want to verify it, you just want to find bugs. That's good enough for now. So you might employ a bounded model checking engine. And the bounded model checking engine essentially takes the verification problem and translates it to a logical satisfiability problem and then uses some off-the-shelf solving technique. Now, usually a BMC engine is not just an encoder, but it also uses something like a static analysis to either generate encoding in the first place or to generate more efficient encodings. Now, if you want to argue about concurrent programs, this problem gets a lot harder here, because now we actually need to think about how threads communicate in concurrent programs. And the answer to that is typically, well, over shared memory. And now we get memory into the picture. And memory needs what we call a memory model. And now you want to take this memory model also as an input to the verification task. But now this opens up three questions. First, what are memory models? Second, how do we analyze these memory models? And lastly, well, how do we encode them? In this talk, I'm going to answer the first two questions. The third one is also part of the paper, but I don't have time in this talk for this. Okay, so first of all, what are concurrent program semantics? Now, let's look at this very simple program here. It has two threads, the left one and the right one, and it works over shared memory, the variables x and y. And somewhat atypical, the semantics we associate to this program are actually so-called execution graphs instead of what people usually do, these interleaving semantics. So we look at graphs. And these graphs have nodes, which are called events, essentially corresponding to the instructions of the program. And then they have relations that tell you how these events interact with each other, such as how do they communicate. For example, we have the program order, the black edges here, which essentially just mimic the syntactic structure of the program. So, for example, on the first graph, you see the write x1 is program ordered before the read to y, which is just essentially the syntactic structure of the program, right? Then there's a coherence order, which I just explained on an example here. You see let's take the first graph here. Initially, the memory value of x is set to 0, and at some later point in time, this value is overwritten and set to 1. And this is what the coherence order essentially models, the order in which the memory is overwritten. Each memory cell has its own coherence order. That's why x and y here are independent. And lastly, there's this read-from order, which just tells you where does the load take its value from. Okay, so it connects the load and the store. Now you might be wondering, if you look at the first execution, is this actually possible? Like, can this happen? You see both threads here read the value 0, but if you then try to come up with an interleaving that leads to this value, this outcome, you will say this is not possible, because one of the threads starts first and sets some memory value to 1, then the other one cannot see this anymore, right? But then you could also say, well, yes, of course, this outcome is surely possible because maybe your compiler reorders the code during compilation, since it thinks these accesses are independent, or the CPU does out-of-order execution and just executes the code in a different order. Now, to model this, we use so-called memory models, or the full name, memory consistency models. And they simply answer the question, given a program execution, is it consistent with how the memory works, with how the buffer structure of the memory works, and how the CPU reorders executions and so on. And the idea is simply to look at the shape of these graphs and of these execution graphs and make a judgment based solely on the shape, not on the data in the graphs. And there exists a language to formulate these memory models called the CAD language. Now we need to take a quick look at the CAD language. So the essential idea is to take these relations you already have, these, we call them base relations, like the program order, the read from, and the coherence, but there can be more. And then simply define new ones using relation algebra. So you can union them up, you can intersect those relations whatsoever. One problem is that you can also introduce recursion, so you can get nasty relations there. And lastly, you can formulate constraints on these relations, such as some relation has to be acyclic. If this constraint is not satisfied, then the execution is invalid with respect to the memory model. It's not consistent with the memory model. That's the idea. To look at an example, here's the sequential consistency model, which amounts to the idea of interleaving instructions. And if we look at the execution graph there, and then simply evaluate the relations, we get to the following happens before relation graph. You don't need to follow why it looks like that, but I mean, it's relation algebra, union, just some unions and compositions, right? Then we can evaluate the axiom, or the constraint, the acyclicity constraint, and it says, well, this cannot happen. So this is invalid. This execution is not allowed to happen, okay? But then if you look at more realistic memory models that incorporate, say, store buffering effects of actual hardware, then you will find out, oh, sorry, there's a little mistake on the slide. I don't know why. So some real models will say this is perfectly fine with how the memory works. Due to store buffering effects, you can get this strange outcome. Okay, that's the idea of the CAD language. Now now you combine this semantics with the program, and you just simply cut off all the executions that do not are inconsistent with respect to the memory model. And this is how you get sort of the combined semantics of program plus memory model. Okay, so now we want to do static analysis. And we want to do some very simple static analysis, actually. Given the program and this CAD model, we simply want to find lower and upper bounds for all these relations over all possible executions. So you can think of this as an interval abstraction, but on the level of relations instead of like integers, for example. Now, here is a very simple example. Say we have this set of 3 execution graphs. The lower and upper bounds would look like this. For example, for the read from relation, there's not a single read from edge that is common among all these graphs. So the lower bound is empty. The upper bound is simply 4 possible edges that you collect from all these graphs together, okay? On the other hand, for coherence and the program order, you will see all these graphs match, so you have an upper bound and lower bound are equal. There's no difference, okay? Of course, you can also do this for these derived relations in the memory model, so you can also find lower and upper bounds for the from read and happens before relation. Okay. Now, it looks very simple, this abstract domain, but there's a little trick here. Because if we look at the lower bounds, we might ask the following question. Say we have this program here which has conditional execution, which is typical in all programs, right? You have some conditional branching. And look at the 2 following execution graphs that are potentially in the semantics of the program. You might say, well, the lower bound of the program order relation is this AB edge, because this is the one common among all the graphs, right? But this notion is too strong because most code and programs is conditional. So you will never really find too many edges that are really common among all program executions because they simply execute different code. So what we did is we relativized this notion of lower bound to just say such an edge in the lower bound means this edge is always there under the assumption that given that the events are executed in the first place. So this is lower bound is sort of relational. It connects the edge variables or these edges to the execution of the events. Okay. So this then also requires us to incorporate some control flow reasoning to work over this domain. Now let's look at abstract computations. So we have our domain, and now we want to compute things. And the idea is that the program restricts the base relations, because like a read from X can only read a value from a store to X, but not from a store to Y. So, for example, you can exploit alias information. You can exploit alias information to get information about the read-from relation, about the bounds on the read-from relation. And in general, you can incorporate many program analyses to give some restriction on the base relations. And then these restrictions is what we propagate upwards to the derived relations. And interestingly, the derived relations are then also constrained by the memory model constraints. And this is something we can propagate downwards. And this is what we did in our work. To give you an example, there's a very trivial program. It's not even concurrent. So there's no magic. It's arbitrary code. But it has these 6 events, okay? If you unroll the loop 3 times. In the beginning, the upper and lower bounds are trivial. I'm not going to give you the full graph because, I mean, you don't see much. It's the complete graph. But then we take the program information as input, and it tells us the following. The program order is fixed. So we have a lower bound that is precise because the syntax is fixed, so the program order is fixed. But with respect to read from and coherence, we don't know much. So these dashed edges are the upper bound, okay? Everything can be connected with everything else. Now we can propagate this information upwards, and get the following happens before graph of possible happens before relationships. Now we can evaluate the acyclicity axiom, and it tells us none of these back edges are actually possible because they would contradict the lower bound we have for the forward edges. So we would get a cycle. So all of them are gone. And now we can propagate this information also upwards again, downwards, sorry, and remove all the backward edges in the original relations. So there cannot be any backward coherences or backward read-from edges. Interestingly, we can now evaluate the program again because the coherence order is actually a total order. It has to order the store somehow. And we just excluded one possibility, so the other one must be true. It is now part of our lower bound. And interestingly, also the second read you have here, because it has only one possible target where it can read from, this one has also to get fixed, so it's a lower bound as well. And you can do this thing again, propagate up and down, and eventually you will have it completely fixed, which is no surprise because this is a single-threaded program, fully deterministic, so there's nothing open in the end. Everything is fixed. In concurrent programs, it's not so. We get actual differences between the lower and the upper bound. Okay, once we have this information, we want to exploit it. But, well, for that, check our paper. But we use it to generate more efficient SMT encodings. So let's come to the evaluation. We've implemented the analysis in our bounded model checker, D'Artagnan, which takes these memory models as an input in addition to the program. And D'Artagnan already has some static analysis because without any static analysis, the problem does not work at all. Like solving it is not going to work. But this older static analysis was not founded on abstract interpretation, so it was ad hoc. It had no lower bounds, and it did not have the idea of propagating information top-down, just bottom-up. And it has 2 different solving strategies, one which generates a full encoding, and one which does generate an encoding iteratively in a lazy way. Now, to give you sort of the gist of the evaluation, we have evaluated this on verifying logs and log-free data structures under the ARM and RISC memory model, as well as kernel code of the Linux kernel memory model. And if you look at the red boxes, the top box is always the old result of the verification time without our new analysis, and the lowest row is the improvement. So, for example, for ARM, we could verify our test suite in 20 minutes instead of 30 minutes. And on the Linux kernel in the Linux kernel, we also got an hour faster in the eager encoding. And even the lazy encoding scheme had some profits from the static analysis. Okay, to summarize, we give a new abstract domain for relations. It's admittedly an easy domain, but with a little twist on the lower bounds. And we give an abstract interpretation based bidirectional analysis in the sense that it propagates information upwards and downwards. And we show how to use it to improve the SMT encodings. Thank you.
Okay, we have time for a couple of questions.
In terms of the evaluation, can you go back a little bit?
Yeah, sure.
Quick question, what are you verifying here? Where is the specification?
Okay, so we used C implementation of logs and log-free data structures, and we compiled them down to ARM and RISC. And for logs, we check if mutual exclusion holds.
Okay.
And for log-free data structures, we essentially check that multiple push and pop operations, say, do not interfere. So if you have multiple threads that are pushing, no node gets lost during the push. Everything comes to the...
And how large is the code for some cases?
I mean,
how many lines, let's say?
In lines of code, it's hard to say. I mean, qspinlog is from a Linux kernel, so it has hundreds of lines of code. The other ones, they're quite small, but we used like 4 threads, and so we scaled it in terms of number of threads. In number of memory events that are happening, so store and load operations, it should be around between 100 and 200 load and store operations. Yeah.
Okay, I'll ask a question. I was trying to think about how you would handle loops and recursion, because then you're going to have a cycle just in the control flow. So do you have to do your bounded unrolling and then do the abstract interpretation?
Yes. I mean, sure. So we do this after the unrolling, since we do bounded model checking. But otherwise, you would have to say, maybe I can show it in some. If you had such a graph, you could start to merge nodes together. So if you have a loop, you just have one representative for all the occurrences of this event. So you compact it. But then, well, the bounds will be less accurate, of course.
Right. But this should mean that you never have to do any widening or anything like that because you don't have any cyclic control flow.
No, we always reduce it to some finite setting, I would say, and then so we don't need to do this.
Yeah. Any other questions?
Oh, sorry.
Okay, let's thank the speaker again.